Good morning. How is everyone this morning?
Good.
Great.
Super. Are there any questions? Okay, I think if you aren't in the class now, you probably will not get into the class, but I want to check. I think that I made it possible for everybody that's a senior to get in the class. If there's somebody that's a senior that needs this class to graduate, and I haven't, and you aren't enrolled yet, please send me an email right away. Okay, Sarah, are you here?
Yes, I'm here.
Great. Would you like to tell them about the schedule?
Yeah, sure. So the MSI schedule is out. So I'll be holding tutoring sessions starting this Sunday, April 4th. So Sunday's tutoring session will be from 7:45 p.m. till 9 p.m. And then there will be 3 tutoring sessions throughout the week on Tuesday from 11:45 till 1 p.m., Wednesday from 12 to 1:15 p.m., and Thursday from 9:45 till 11 a.m. And then these are all going to be on the class website, I believe. So yeah, look forward to seeing you all there.
Great. Yeah, the schedule is on the web page now. Okay, so we've been talking about sets, etc. So today let's talk about more of the etc. And namely propositional logic. Okay, so what's a proposition? It's a statement that's either true or false. We have a whole bunch of standard symbols that are set up to make it easy to reason with these things. For not, we use this. Got a thing called implies, but that name can be misleading. We'll see why. And we have an if and only if. And we have some constants. Okay, these should be T and F for true and false, but also can use, if I'm going to say true or false, let's say 1 and 0. These are a lot easier to write, so we'll frequently use those. Variables are usually written in uppercase. And the definitions of these things, these words are English, so we tend to think of them, but we have an idea already what not means and what and means, what or means, and what implies means. Those intuitive ideas that we have work pretty well with the not, the and, and the or, but with the implies, you could get misled. So we'll talk about that a little bit more. But you should really think of the definitions of these things as being given by truth tables, and the definition should be just exactly what the truth table says. So in that case, then for truth tables, usual way of doing this is we have all of the possible states of the world. In other words, for the variables under discussion, the different truth values they could have, combination of truth values. So for not, the definition, which of course I know you all know, is that quite simple. Okay, for the other ones, we have two propositions involved. So our possibilities are like this. And the value for P and Q, this is only true if they're both true, right? Here, all the others, it's false. And for P or Q, if either one of them is true, then it's true. The only place that it's false is here.
Professor?
Yes.
Wouldn't the P or Q be the other way around? Like what? I'm sorry, 0, 1, 1, 1?
You're absolutely correct.
Okay.
Okay, so here's the one that could be troublesome if you think intuitively about it. What this says is, it is not the case that P is true and Q is false. P is true, Q is false would be right here, right? So it's saying this is false. And that's all it's saying. We'll talk a little bit more about that later. And the if and only if is that they have the same value. So it's 1. And we might as well define here a couple more things that are quite useful. One is tautology. A tautology is something that is true for every possible state of the universe. So here's an example tautology. This is the Hamlet tautology. So this is true for every possibility. Contradiction is just the opposite of the tautology. It's something that's true regardless of the state of the universe. I mean, excuse me, it's something that's false. So for this, it's going to be false for all of them. And of course, this follows just from the definition of the not and the and. Any questions on that? Okay, back to the P implies Q. I find it useful, at least when you're first learning these things, which I know you have all learned them. But let's say we have two things here. And we want to say is if X is less than 10, then X is less than 100. Okay, I think we all feel quite comfortable with this being a valid statement. That this is definitely represents what if then means. Any questions on that? Okay, well, we'll look at for values of X. If X is from 1 to 9, then the P part is true, right? And the Q is true. Okay, if X is ten to 99, then it's certainly not less than 10, right? So that's false, but this is true. And if X is 100 or more, then this is false, and this is false. So notice the thing that we don't ever have showing up here is the case of false. Yeah, we don't have false true. Excuse me, we don't have true false. We definitely have false true. Okay, so we can see here that we consider this thing to be true, and yet these are situations that could be the case depending on the value of X. So certainly we get this interesting thing that if the Q is true, it doesn't matter whether X is true or not, this is still true. And so what it's really saying is that this is not the case, that you'll ever have X being true and Q being false. I don't know, does that help with that interpretation? Okay, also notice that another way of saying that it's never the case that this is true and this is false. We can write that with our logic like this. It's not the case that P is true and not Q is true. In other words, P is true and Q is false. This is the same thing as P implies Q. In fact, if we do a truth table for the two of them, we get exactly the same entry. Okay, this is also the same thing as not P or Q. Okay, any questions on that? Okay, so what are these things? One of the things that these are good for is to determine what are valid arguments, such as We're quite used to this one, right? P implies Q. P, therefore Q. Okay, a valid argument is, an argument is valid if you take the conjunction of the premises with the negation of the conclusion. If that's a contradiction, then the argument is valid. So let's take a look at this one. Okay, so the first thing we're going to look at is the truth values for the premises. We only have two here. One is the P implies Q. That's 1, 1, 0, 1. Just for the purposes of making it clearer over here, I'm going to repeat P. And what did I say before? I said if the conjunction of the premises with the negation of the conclusion is a contradiction, then the argument's valid. So what's the negation of the conclusion? It'd be not Q. Okay, any questions so far? This is just premise 1, premise 2, conclusion. Now we want to look at the conjunction of these three things. So this is going to be looking at, this value here should be P implies Q and P and not Q. Okay, well, this conjunction has three components. We know this is going to be true only if all three components are true, right? That's not the case for any one of these. So this is why we know that this argument is valid. Okay, somebody has their mic on. Any questions about that?
So because the very right column is all zeros, that means that the premise 1, premise 2, and conclusion is valid?
It means this, yeah, that this argument is valid.
Okay, why is that the case when the things on the right are all zeros?
Because we're saying an argument is valid if the conjunction of all of the premises and with the negation of the conclusion is a contradiction. In other words, it wouldn't matter what the truth values are for the variables if it's the case that regardless of what those truth values are, that the conjunction, in other words, saying all of the premises are true and the conclusion is not true, that is false in every possible state of the universe.
Okay, and let's say that one of these columns on the right, or one of these rows on the right, had a 1 in there. Would that mean that this conclusion, this argument is incorrect? So let's say like the
Depending on
first
what
row.
I think it would say it's not valid.
Okay, can you repeat that?
I wouldn't say that it's incorrect. I'd say it's not valid.
Okay, okay.
Yeah.
All right, thank you.
Sure. Here's a bunch of valid arguments. We just verified this first one is valid. All of these things have some names, which I don't think it's worth learning. They're Latin, and they come from an ancient way of looking at these things. This is called modus ponens. Okay, so let's see if we believe these arguments without verifying it with our truth table to show that the conjunction of all of the premises with the negation of the conclusion is a contradiction. Okay, so this one, I think you were willing to believe this before I put you through the tedium of of proving that it's valid by the definition of validity. Okay, now this one, this P implies Q. Q is not true, so that means that P can't be true. Everybody feel comfortable with that? Okay, if P implies Q and Q implies R, even with our special definition of what implies means, we will get the case that the P then implies R. Okay, this one is certainly a valid argument. It may seem a little strange, but it's sort of saying if the premise is false, the implication, well, or let's put it this way. This is if at least one of these is true and P wasn't true, then Q's got to be true. So I think that's a good argument for that. Okay, with this one, if P is true, well then certainly P or something else, it doesn't matter the value of the other thing. Since P is true, this is true. Okay, if both P and Q are true, you can certainly conclude from that Q is true. You can conclude from that P is true too, right? Okay, remember these are premises in an argument. So this is a statement that P is true. This is a statement that Q is true. Therefore, you can conclude that the conjunction of the two is true. Okay, so if you have these as premises, not P or R and P or Q, well, not P is true or P is true. One of these has to be true. And so, and from that you can get that the Q or R must be true. Any questions on that? Okay, so let's say you you had a situation where you have a premise that P is true, and another premise is not P is true. Then from this, if not P is true, in other words, if we've got, let's see the argument that I want here. What I want to go to is from the fact that not P is true, then it must be the case that not P or, let's say, X is true, where we don't know the value of X, right? Okay, and that one followed from this one right here, right? If P is true, then P or anything, this is true. So if not P is true, then not P or anything is true. Okay, but what is this thing equivalent to? This is equivalent to P implies X. You with me? Okay, but now I've got P is true and P implies X. Therefore, X is true. What's the problem with this? X could be anything.
You have P and not P on the first two lines.
Yeah, this is a premise. P is true. Another premise is not P is true.
So that means it's a contradiction, right?
Yeah. And what did we just show comes from that? That if you have a situation where both P and not P can be true, you can prove anything is true. Anything. That was the problem that Russell's paradox introduced into logic. Okay, and of course now we know we can avoid Russell's paradox. So we don't have to worry about that. Okay. I think that's probably all of the logic things that we're going to be concerned with as far as any formal representation of it. The next thing I want to talk about is cardinality, which with finite sets is just basically the number of elements that are in a set. So if it's finite, then this is the number of elements in A. So of course, if we have the empty set, we know that's 0, right? Cardinality is finite, or if it's not finite, then it's simply infinite, right? If we're dealing with finite cardinalities, then everything, I think your intuition will not lead you astray. When we're dealing with infinite cardinalities, then it turns out that maybe there's some different sizes of infinite cardinalities. There's a really old book that's called 1, 2, 3 Infinity that the physicist, I think his name was George Gamow, wrote. He was a popularizer of science. And he talked about a tribe or a group of tribes that are in Africa. I think they may still be, and they have an interesting language. And their language for numbers contained a word for 1, a word for 2, and a word for 3. Didn't have 4, 5, 6, or any of the other numbers. What they had for that was many. You know, so this is 1, 2, 3, many. which should serve their purposes quite well. So they didn't get into complex accounting or anything like that. Okay, well, we've got kind of a similar thing. We've got all of our finite numbers, and then we say infinity. Well, for the Hottentots, say that one Hottentot had a bag of red rocks, and another one had a sack of fish or something like that. And they wanted to make an exchange, but they wanted it to be 1 for 1. That if, you know, however many red rocks, which must have been pretty valuable, there should be that many fish. Well, how could the Hottentots resolve that? How could they compare their 2 bags of many things to see if they were equal? Any ideas?
By weight?
Well, a red rock probably doesn't weigh the same as a fish. You know?
Did they just use a trinary system? Like many, many, one, many, two, many, many?
I've never heard of that approach. That might be interesting. They'd be inventing positional notation, right? Even the Romans didn't do that, right? Okay, how about?
Oh, do you split into? Do you like split into groups by 2s and then?
Yeah, by pairs. We'll take a rock out of one sack, and we'll take a fish out of the other sack, and those match, right? And we'll do that again until we exhaust the contents of the 2 sacks. And if they exactly match, you know, every place I've got a rock, I've got a fish. Every place I got a fish, I got a rock. Exactly. Then they could be pretty confident that they had the same number of things in each sack, right? That's called a one-to-one correspondence. Okay, and it turns out, hey, we can use that approach to talk about infinities. And we will say that there is such a thing as countably infinite. And uncountably infinite. Okay, and so with the countably infinite, what we have in one sack is the natural numbers. And we will say that any set that we can put in a one-to-one correspondence of its elements with the natural numbers is countable. In fact, notice, you know, that when you usually when you count things, that's exactly what you're doing. Is you've memorized what the natural numbers are, and think of pointing to things. You say, oh, 1, 2, 3, etc. And then so you're creating this one-to-one correspondence with, in that case of actually counting, with a finite number of the natural numbers, and you say that the last one you ended up with is what we say is the size of that set. Okay, so by the definition then of countably infinite, what we're saying is you can put the elements of the set in a one-to-one correspondence with the natural numbers. Well, then certainly the natural numbers are countably infinite, right? Okay, how about the even numbers? There's certainly an infinite number of them, right? Are they countably infinite? Remember, what's our definition? That you can put them in a one-to-one correspondence with the natural numbers, the whole set of natural numbers.
Yes, they are countably infinite.
You bet. And here's our correspondence. Etc. So if you're asked to show that that some set is countably infinite, this is all you need to do is to show a one-to-one correspondence. Okay, it also would turn out then to be the case if it's possible for you to list the elements of your set in a list, then it's countable, right? Because the natural numbers just correspond to first thing in your list, second thing, third thing, etc. Okay, we get the strange thing with this when we say that that all of the natural numbers has the same cardinality as only half of them. That seems, I'm sure that seems a little weird, that these are really the same number. But think back to that very simple reasoning that if we take things out of the sacks one at a time, and we keep that matching going for forever, that there must be the same number of elements in the two sacks. Okay, so that's the even natural numbers. So you could easily do this with the odds, right? Or even, the numbers mod any number would all work out. Okay, with different series or sequences of infinite numbers, like for instance the Fibonacci series. Is that a countable set of numbers? Yes. We can, any series you could do with saying this is the first element and here's a little rule for elements after that produces a one-to-one correspondence. So you can definitely do it with the Fibonacci series. Okay, what about let's say rational numbers? Are they countable? What do you think?
No.
Somebody said yeah.
So I said no.
No, okay, great. So you're challenging me to show you a one-to-one correspondence, right?
Exactly.
Yeah.
He is challenging you.
Okay, let me get a little drink of water here and I'll do this great task. To make the reasoning clear, and I'll take a little simpler case. Let's just say positive rational numbers, okay? Okay, rational numbers are what? It's P over Q, where both P and Q are natural numbers. Okay, and so if I let this be the P's, and we got to start our our Q's at 1. We won't allow the 0. So this is 1, this is 1, this is 1, this is 1. Here are the halves, etc. So you can see that these correspond to the points on this grid. Well, I haven't shown a one-to-one correspondence yet, right, with the natural numbers. But if I can put these things into a list, and you know how to generate the list, then I have put it into correspondence with the natural numbers. Okay, and the way I'm going to do the list is, this is going to be the first one in the list. Then we're going to do this one and this one. And then we're going to do this one and this one and this one. And then this one and this one and this one. So here's my, I think you can continue this list now, right? So this is the first rational number, the second one, the third one, the fourth one, the fifth one, 6th, 7th, 8th, 9th, etc. So we do indeed have a one-to-one correspondence here. So conclusion, rational numbers are countable.
Professor?
Yeah.
Is there a closed form way to describe that?
You know, I saw one once, and I hadn't been able to find it again. One of the things that you run into, oh, we could do that for this, but another little subtlety is, I've actually seen a case where, in mapping the natural numbers to one of the rationals here, notice that we'll get repeats of a rational number, because we consider, 1/2 and it's etc. is the same thing as 10/20s and etc. Okay, I've even seen an algebraic expression for the correspondence that avoids that.
Wow.
Okay. But yeah, for us, if we're comfortable with, I showed you how to make a list, that then the correspondence does exist, even though I haven't shown you an algebraic thing to give you what corresponds to n.
Okay.
Okay.
Excuse me, Professor.
Sure.
So if a set is countably infinite, would all subsets of that set be countably infinite too?
Yeah, but that'd be a theorem we'd have to prove, right?
Yeah. Okay.
Okay, but it turns out, and how you say those words, it'll turn out that if a set was countably infinite, and we talk about the set of all subsets of that set, that won't be countably infinite. But it'll be a little while before we get to that.
Okay.
Okay, so what's the next thing we think of? We've got integers, we've got fractions, we got rationals. What's the next kind of number that we're likely to be? Oh, wait a minute. Yes. We had the rationals. How about integers?
It should be yes.
Yeah, it's yes, but now we've got well, we got 0 and we've got 1 and we got 2, 3, da 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 da. We got -1, -2, -3, etc., etc. So there's definitely an infinity of these things, right? How can I put it in one-to-one correspondence with the natural numbers? Or let's say that, you know, the easy thing is to show how to make a list that includes all of these integers.
Do you do 0, 1, -1, 2, -2, and so on?
Got it. Right. So does everybody feel comfortable that that we've got a list, a way to generate a list of all of the integers? Okay, so we've got the natural numbers, we've got the integers, we've got the fractions. What's the next thing we might think about?
So for this integer list, you'd say this is uncountably infinite? Or sorry, countably infinite?
Yeah, yeah.
Okay.
Yeah. And this one, it's coming up with the expression for it is it's not too hard. I think this works. This is the floor notation. Yeah, so there's the expression of the one-to-one correspondence. And this will actually correspond to exactly what we just did.
All right, thank you.
Sure. Okay, what about, let's say, strings of zeros and ones? Okay, well, there's the empty string, right? And there can be, and then I'm going to do strings that this had a 0 length. I'll do length 1 strings. There are only 2 of those, right? And I'll do length 2 strings. And I could do length 3 strings. You know what this is going to be, right? This will be all possible strings of zeros and ones, right? So how do I put this in one-to-one correspondence with the natural numbers?
Just start counting from the empty string all the way down.
Yeah. Let's do that this way. So this one we want to correspond to 1, right? We want this one to correspond to 2. But being computer geeks, we're going to use binary, right? So this one corresponds to 2. That's 2 in binary, right? And this one corresponds to 3. So there's 3 in binary. And this one corresponds to 4. So this is going to produce this series of natural numbers, right? 1, 2, 3, 4. And look how we can get each one of these from this. We just append a 1 to the front of each one of these things. And that's the rule that'll produce that one-to-one correspondence. But now, what about the real numbers? Okay, well, the first thing is, let's make it a little simpler without really losing anything, and just talk about the real numbers between 0 and 1. So we can consider the numbers between. Zero and 1, let's say. So we need an argument for why can we do this? Okay, well, here's a number line. Let's put 0 right here. Now these points represent the real numbers. These are positive ones, these are negative ones. Now what I want to show is a mapping, a one-to-one correspondence between these real numbers and only the real numbers between 0 and 1. That would show they have the same cardinality, right?
Yeah.
Yeah. Okay, so how can I do that? Okay, well, let me go up here. I'm going to draw a half circle here. Okay, and let's label this one. Here's 0, and here's 1 on this semicircle here. So now what I need to show is a one-to-one correspondence between points on this and points on the whole line. Okay, well, we get that by this point corresponds to what point on the real line? Well, we find that out by going here to the center of the circle and a line through this point. And where it hits here is this corresponding real number that corresponds to this real number. So all of these real numbers between 0 and 1 with this little construction can be put in a one-to-one correspondence with all of the numbers on the complete line, right? So we could limit our attention to just the numbers between 0 and 1. Okay, we've been talking about things that are countable infinities. Okay, do you think that this is a countable infinity? And I'm going to pull some trick here and show it. Nope.
No.
What we can actually show that the real numbers are not countable. And we've got 10 minutes to do it. Okay, so I'm just talking about the the real numbers between 0 and 1. Okay. Now we're going to prove this with a technique that's called proof by contradiction. I'm going to assume something and show that then logically what follows from that is something that can't be the case. And what do we conclude from that? The original assumption must be wrong. So let's assume that the reals between 0 and 1. I might get a little sloppy about the about whether this is open or closed or semi-closed. Are countable. Okay, then that means that it'd be possible to make a list of them, right? So let's make the list. Here's the first one, the second one, the third one, etc. Okay, so we can think of these things as these numbers in here of being like point, and then we have some digits out here, right? Like maybe this 1 0 1 1 1 0, etc. And then the next one is maybe 1 0 1 0 1 1, etc., etc. And so maybe the third one is 0 1 1 0 0 0 1 1 1, etc. Okay, so I assumed that they're countable. In other words, assume that we can that a list can be made. And now what I want to show is that if we had such a list, we can show a real number in here that's not in the list. In other words, I assume that they're countable, which means a list can exist. And I show if a list does exist, it doesn't contain every real number. If the list doesn't contain every real number, then I certainly didn't show that it was countable, right? So how, given a list, how do I come up with this number that can't be in the list? Okay, I make the first position of it opposite this one. So it'll be a 1. The next one opposite this one. So it'll be a 1. The next one opposite this one. So it'll be a 0. So I think you can see how I'm generating this number. Okay, well, notice this number by this construction is different from at least one of the numbers in this list. So it can't be in the list, but yet it's a real number. That's the big contradiction. Therefore, that original assumption that a list could be made, in other words, the assumption that they are countable, can't be true. Questions? This argument is called, well, part of it is we have an argument by contradiction. Another characteristic of this one that we'll see in some future proofs we do too is called a diagonalization argument. And that comes from the fact that we're making use of the values on this diagonal in our argument.
Sorry, Professor, I don't know if I missed your explanation, but why is the diagonal specifically important? Why can't we just pick random values? To construct our string, I mean, that's not in the list.
I don't think you can't just make them random. Let's see what would happen if we did this. You could do this. You could say randomly pick some position in the number and make that position in the thing that we're generating opposite. Okay, if you're doing this, randomly picking some position, then are we guaranteed that we will talk about all positions? I'm not sure. I don't think so. But if you can do any technique that takes one element of one of these, and in your number that you're constructing, you guarantee that it can't be the same for everything in the list, that will work. And I think you can come up with other ways too. But the simple thing is to just go down the diagonal. Then we've talked about every possible position. And we've made the number we're constructing different from at least one of the numbers in the list because of that fact.
So it's not that the diagonal specifically is important. It's just an easy way of trying to find a one-to-one correspondence.
Yeah, I think we could come up with another way of picking these things, but it will still end up being that when we generate this number, we have to have some way of guaranteeing that this position in the number is different from at least one thing in our big list of numbers. Any technique we'd come up with that would guarantee that, to take any position, and here, say it was this one. We just have to be able to guarantee that there's at least one number in our list that has a 1 here instead of a 0.
That makes sense. Thanks.
Sure. Okay, so you've got a homework assignment to work on. Are there any questions on it? Then have a good weekend, and I'll see you on Monday.
Professor, can I ask a quick question about getting the videos for the lecture, like the lecture recordings? Are we supposed to ask for every single lecture, or if we just ask you for it, we have access to all of the future and previous lectures as well?
No, they aren't. I'm not making the recordings of all of the lectures generally available.
Okay.
They are for certain DRC students that have that accommodation.
Mm-hmm.
Okay, but there are two things that I am doing to help a bit here. One is you can see a recast of any one of the lectures by signing in the following day at 9 p.m. And I've recast it, and I'm also available to answer questions. The primary motivation for that was for people that are in a different time zone, but anybody can do that. The other thing is, since you might have to miss a lecture, and I'll be quite glad to give you access to that lecture if you just tell me I missed such and such a lecture, and give you a reasonable access so you can see it.
Right. So we'll have to ask for a specific lecture, not all of them.
Right.
Okay. Thank you.
Sure. Any other questions? Okay.
You also, I remember you mentioning possibly giving us some copy of the notes that were taken during lecture. Would that be on the course webpage or on Canvas?
It's on Canvas.
Canvas, okay. Thank
Okay,
you.
and so far it's just the first set of notes. So there's, I think, probably all of the stuff that I've talked about before today is in that first set of notes. And the next set will be available on Monday.
Thank you very much.
Sure, no problem. Any other last minute questions? Okay, then.
Oh, I just want to, so attendance, is that no attendance quiz or whatever?
No, that's just for the first day.
Okay, thank you.
Yeah. Any other questions? Okay, again, if you're a senior and you're not formally enrolled yet, send me an email right away.